Hello, I am Rahul Manoj and I will be talking about my science project. First, let us look at Laguerre polynomials. So this diagram represents the first five Laguerre polynomials of the series. So what is the Laguerre equation? Laguerre equation has its application in solving Schrodinger's equation for the radial part of the equation. So what we do in this is a normalization of the Laguerre polynomials, which are nothing but the solutions of the Laguerre equation, which is of the form x y double dash plus v nu plus 1 minus x y dash plus lambda y equal to 0, and the solution for which is given by the second equation. So we start the simplification of the derived result from the Hamiltonian's equation for only the radial part, which is of the form d by dr r square d capital R by dr minus 2mr square by h bar square into vr minus e into r is equal to L into L plus 1 r. We can simplify this equation by isolating the leading derivatives by substitution. So what we get is d square u by d rho square is equal to 1 minus rho naught by rho plus L into L plus 1 by rho square u. From this, we get an asymptotic solution, but as rho tends to infinity, the general asymptotic equation loses the second e raised to p term and reduces to just L into L plus 1 u by rho square. By simplification, we get that the resulting characteristic is 1 plus minus 2L plus 1 by 2 root of L into L plus 1, with solutions being gamma rho raised to L plus 1 plus x rho raised to minus L. Reformulating the equation further, rho raised to L e raised to minus p in brackets minus 2L minus 2 plus rho plus L into L plus 1 by rho nu plus 2 into L plus 1 minus rho dou v by dou p plus dou square v by dou p dou rho square. The radial equation for this is g square u by dou rho square is equal to 1 minus rho naught by rho plus L into L plus 1. We rewrite the equation in terms of v and perform typical derivations, so the equation becomes mu rho is equal to sigma j is equal to 0 to infinity 2 raised to j by j factorial p raised to j is equal to e raised to 2p. From this, we get a new recursion equation which looks like this. The j plus first term is equal to 2 into j plus L plus 1 minus 2n by j plus 1 into j plus 2L plus 2 into aj. The asymptotically suggested equation thus gives us a starting point for its completing function, and by applying simple chain rule differentiation to the kernel, omega is equal to e raised to minus x raised to q, from which we get e raised to x omega double dash at q is equal to 2 is equal to 2 minus 4x plus x squared. Then on we get the correct solution form, which is v raised to p at q minus p is equal to this. This finally, when we substitute it into the radial equation, gives us the final equation, which is n by an, r by an raised to L, e raised to minus r by na, L raised to 2L plus 1 at 2r by na. Here n is a normalization factor, which we have to find using normalization of Laguerre polynomials. Given that ln x is equal to e raised to x by n factorial d to the n derivative by dx square of x raised to n into e raised to minus x, we note that n plus 1 L of n plus 1 x is equal to 2n plus 1 minus x into ln of x minus L n minus 1 x. Here we can see that using the Laguerre polynomials can be used for finding the normalization factor. Finally, after finding the normalization factor and resubstituting into the RR value, we get the final radial equation as this, which is RR is equal to root of n minus L minus 1 factorial by 2n into n plus L factorial into 2 by na the whole cube the whole under root e raised to minus r by na, 2r by na whole raised to L, L raised to 2L plus 1 into of 2r by na at n minus L minus 1. Let us see some other applications of Laguerre polynomial. They have come under use in many other areas of quantum mechanics like Wigner functions of oscillator system, a Morse potential, and in 3D isotropic harmonic oscillator. Now let us see Hermite polynomials. This is another orthogonal polynomial sequence just like the Laguerre polynomials and Legendre polynomials. This just means that any two terms in the sequence is orthogonal to each other. Let us see its application in quantum mechanics. First, let us see what quantum mechanics is. It is simply the mechanical analog of the classic harmonic oscillator. This is because an arbitrary potential can be used, usually approximated as a harmonic potential at the vicinity of a stable equilibrium point. It is one of the few quantum mechanical systems for which an exact analytical solution is known. Basically, the Schrodinger's equation is analogous to the classic harmonic oscillator. So if we consider the potential to be of the form Vy is equal to y square, and therefore we can consider the following equation, which is none other than the Schrodinger's equation. We make a change of variable y is equal to kx, transforming the equation into d square psi by dx square minus 2m k raised to 4 by h bar square into e minus y square psi is equal to minus 2m k square by h bar square e psi. By choosing an appropriate constant for k, we get d square psi by dx square minus x square psi is equal to minus beta psi, where beta is equal to 2m by h bar square raised to half e. Here equation 1 is a second order differential equation with variable coefficients. Upon simplification, we find that the solution of the equation to be psi nx is equal to psi n psi star into x hfx. Here hfx is the function to be determined. We do this by substituting psi n of x given earlier into the equation 1, and we obtain h double bar minus 2x h bar plus beta minus 1 h is equal to 0, which is the standard Hermite equation. Other applications of Hermite polynomials. Combinatorics, probability, and system theory also uses Hermite polynomials. Now let us see moment of inertia matrix. Inertia matrix has multiple applications. It has been used in understanding the dynamics of spinning top and calculating eigenvalues in quantum mechanics. Some places where this is applied is to find whether all eigenvalues of an operator are real if the operator is Hermitian, to show that an inertia matrix is Hermitian or not, is another application. Let us now understand how it is used in understanding the dynamics of a spinning top. Let us first look at the prerequisites. We know that every rigid body has three orthogonal principal axes. These are the eigenvectors of the inertia matrix with the corresponding eigenvalues giving the principal moments. The basic thing to note is an ideal case when the coordinate axis coincides with the principal axis, then the inertia tensor is diagonal. So now let us look at an application. Let us take a motion of a rotating cube, which is a perfect example of a spinning top. We wish to compute the inertia tensor of a uniform density cube of mass m and side s and density given by rho is equal to m by s cube. We get I is equal to ms square by 6 into this matrix, a diagonal matrix. Using parallel axis theorem with the translation of a vector is equal to minus s comma 2 for all three axes. From this, we can conclude that the inertia tensor is not diagonal, so torque is required to keep the cube in motion, that is rotating about a corner, if the axis of rotation is in one of the edges of the cube. Now let us look at Lagrangian and Hamiltonian in rocket mechanics. We shall consider a point mass rocket for this. equation of a point mass rocket in Lagrangian form valid in any coordinate system is derived. The Lagrangian form of the rocket can be used conveniently in the calculation of the rocket motion involving complicated constraints for which the use of generalized dynamical coordinates is advantageous. Let us assume the rocket is moving along some direction with a velocity xi. So the differential equation for this motion would be mxi is equal to m dash ci plus fi. Let us take this as equation 1, where m is the mass of the rocket and is a function dependent on time. M dash is the first derivative of m with respect to time, as the mass of the rocket would decrease when fuel is ejected during launch. There is also a corresponding increase in speed, which is the result of the thrust due to the ejection of mass. Let us take the velocity of the expelled mass to be Ci and Fi be the force applied excluding the thrust force m dash Ci. We can then derive that the kinetic energy of the rocket at any instant is T is equal to half m of t x bar 1 into xi bar. After manipulating and dotting equation 1, we get the following equation. This d by dt of rho kinetic energy by rho of q bar alpha minus rho t by rho q alpha is equal to m dash ui rho of xi by rho q alpha plus fi rho xi by rho q alpha. Let theta be the angle that the straight line makes with the vertical. If xi are rectangular coordinates of the rocket, then x1 is equal to r into sine theta cos omega t, x2 is equal to r sine theta sine omega t, x3 is equal to r cos theta. Here alpha and beta are values ranging from 1 to n, where n is the nth derivative of the equation. Now if theta and omega are constant, equation 2 becomes d by dt of dou t by dou r bar minus dou t by dou r is equal to m dash ci plus xi dou xi by dou r plus fi dou xi by dou r. Now we know that the rocket is subjected to uniform gravitational force and velocity of the expelled mass is also constant and changing constantly, that is, oriented along a straight line toward the apex 0. We also know that Ci is equal to minus C into xi by r from this. Making the required changes to equation 2 per the above, we get the Lagrangian equation, which is mr double dash minus m into omega square sine square theta into r is equal to minus m dash c minus mg cos theta, where mass expulsion is minus km and k is a constant and the initial conditions are t is equal to 0, r is equal to r naught and r dash is equal to 0. Thus the final solution is given by r is equal to r naught plus kc minus g cos theta by omega square sine square theta cos h omega sine theta t plus g cos theta minus kc by omega square sine square theta. Now let us look at the Hamiltonian part of the equation. If equations of transformation contain time explicitly, then the kinetic energy is T is equal to half m dou xi by dou q alpha into dou xi by dou q beta dash plus rho xi by dou xi by dou q alpha into dou xi by dou t q alpha dash plus half m dou xi by dou t into dou xi by dou t. After following the standard procedures and assumptions, we derive the Hamiltonian equation as r is equal to r naught plus kc minus g cos theta by omega square sine square theta into cos h omega sine theta t plus g cos theta minus kc by omega square sine square theta, which is the same as the equation we get from the Lagrangian method.